I'm now recording. By the way, after speaking about not being able to pick you up on this microphone last lesson, it picked up a lot of what you were talking about last lesson. I don't know what went wrong, but if you go and watch that video, you will very clearly hear yourselves talking, which I'll do something about. I'll look into my compression or whatever's going on the microphone to make sure that you're not heard, because no one wants to hear you, really. Huh? All right, today we're going to recap forces on an incline. Now this is kind of the summary, yeah? We've done normal forces on an incline, we've done applied forces at an incline, so if we're actually pulling at an angle, we've done tensional forces, and we didn't look at how they involve an incline necessarily, but we did look at how they can change the direction of forces and what that means for our frame of reference. Remember that if we're over a pulley, yeah, this here is equivalent to this. So if we have a directional system like this, plus plus, and we have a pulley here, this force and this force, FA and FB here, you cannot say that FB is negative and FA is negative. They're not. You need to imagine it being this case. FA is going that way, FB is going that way, or this case. I don't mind which one you think of, but you need to imagine them as acting in opposition to each other. Okay, so pulleys can change the direction of the forces, which can mess with our system or our frame of reference. So keeping that in mind as we move forward. Now today we are going to summarize forces on an incline, and we'll do that with one very clear example, hopefully, forces on an incline, and a bit of a diagram as well to summarize things. A diagram you're probably somewhat familiar with, really. The crux of this is understanding how to set frames of reference in more than just horizontal and vertical planes. That parallel and perpendicular component of a plane is really important to be able to do as well. So we're going to start with, and I was not prepared enough and don't have it up, so give me a second. We're going to start with a nice, neat figure of how we break that force of gravity down into its perpendicular and parallel components, because that's really an important skill for this, and we're going to do it quite a few times. So we'll start with that. Is that the right figure that I want? Yes. Okay. Hello? Thank you. So this is our figure here. So we have our incline, of course, some theta, some ground, some object, has mass, it has a force due to gravity. That force due to gravity has a parallel component, FG parallel, or parallel at all. And I might actually connect my forces here to a point at the center of the mass, which is realistically where we're imagining these forces being applied, at the center of the mass. Now, perfectly perpendicular to the parallel component, of course, is my perpendicular component of my force, and that would extend to about there, I think would be about right. That will be our FG perpendicular to our plane. Remember, we're using this symbol here to mean perpendicular because that's a right angle, and we're using this symbol here to be parallel because that's how we draw parallel lines, okay? So FG parallel and FG perpendicular, and we established that this angle here is equivalent to this angle here. How? Well, it comes down to a bit of sometimes kind of messy angle geometry, but essentially this angle here is the angle in that triangle there. So that minus the 90 degrees that we see here gives us that angle there, okay? If you want me to review that at any point, we can sit down and quickly sketch that up to remember what that is. But this is just the rule we're going to use, okay? And then from this, we can derive that F perpendicular is going to be our cos of our gravitational force. A nice, neat summary here from things we've already talked about. And our perpendicular force is going to come from the sine of our gravitational force. Remembering that when we take cos or sine of an angle, we end up with some number between 0 and 1 generally. So we end up with a fractional amount because we're taking a fraction of that gravitational force, because only part of the gravity is going parallel and only a part of the gravity is being applied perpendicularly. Now, why is this perpendicular component of gravity useful? What does it help us find? The normal force, excellent. Yeah, so this can help us find our normal force. I won't draw this from the center of mass because it would intersect the M there, but we know that it's imagined as being coming from the center of mass. And also, this force of gravity parallel is useful for establishing a relationship between it and, right, commonly opposing the force of gravity parallel to the plane would be the force of friction. Okay, and we can set ourselves into a frame of reference of parallel and perpendicular and look at our net forces and subsequently make predictions and calculations about the motion. And again, as we established last lesson, when we talk about the motion of an object, really we're referring to acceleration. Is it accelerating? Yes, no, maybe so. By how much? Okay, and that should be a calculation. We can talk about velocity. You've got your linear motion formulas. So if you know that an object was at rest but has these forces and it's going to accelerate at this rate, you can find what its final velocity is after x time. And there's going to be questions that come up where you combine all of this. Yeah, you'll be able to take the formulas you use for calculating the ball dropping and what its final velocity is. That projection at an angle stuff can come up on inclines as well. Okay, there's no reason it can't. Same with gravitational potential, which we spent a bit of time talking about. If you're so high on an incline, you know exactly how much kinetic energy you'll have at the bottom purely based off the potential energy you had at the top of the incline. You can use that to calculate the acceleration. You could then use that to calculate the net forces. You can do this in so many different ways. You can go back and forth with all your different formulas. We need a lot of practice to know how to do that. Let's quickly do I think that's enough for that one. Any questions about that figure? Is that pretty clear? Everyone's sort of wrapped their heads around this by now, I hope. This complication, again, will probably continue to confuse you until you do this a ton of times yourself. Yeah. If you wanted to rote learn these, you can rote learn them. Feel free to. If you wanted to do them by derivation every time, you'll have to imagine this triangle as looking kind of like this, right? This is the angle we're given. This is some other angle. And then that FG FG perpendicular is the difference between that and 90 degrees. So it must be that angle, theta, okay? And then you think about what triangle you're drawing. You're drawing a triangle. You've got, you know, this here would be your adjacent to your angle. This would be your opposite. This would be your hypotenuse. So you use cos to find your perpendicular. If you're trying to find this part here, which is the parallel just shifted, you're trying to find with sine. Okay, you can derive that yourself every time if you want. Let's do an example. I think 3E. For anyone following along on the textbook, this is worked example 2.3E, so we're jumping right ahead. One of the last examples on this stuff. And it's going to bring together a lot of what we've looked at, but hopefully I'll prove to you. I might actually just take it to the next page, sorry. Does anyone have that diagram down? If I shift forward? Anyone need 10 seconds? Nope. Forward. Okay. So this is going to bring a lot of things together, but hopefully I'll prove to you that there's nothing particularly difficult about this example here, despite all the different aspects of it, okay? So let's have a look at this. A cart in a mine is dragged up a 20-degree incline by an applied force. Okay, let's stop right there and let's imagine that situation. I mean, if we wanted to do step-by-step process for solving these types of problem, your step one is always going to be what? Draw a diagram, all right? Probably more than one. Draw a diagram every time you feel like you could capture some information very clearly in a diagram. Right? If you can't imagine what this thing looks like visually, you can't solve it. These are geometry problems quite often. If you can't see the geometry of it, you're not going to be able to answer it. So this is a cart moving up an incline, 20 degrees, right? Nothing new here, yeah? An incline of 20 degrees, right? We don't need the end there. By an applied force provided by a hanging mass over a frictionless pulley system, okay? So what that means is there's some mass hanging. This is the mass in the hole, sort of problem, right? There's some pulley at the end here. There's an applied force here, Fa, and that is connected to a hanging mass. What do you mean? It's frictionless. Yeah. No. It still changes the direction of the force. Yeah. It just has no effect on that force. It doesn't change it. So this is going to have some force due to gravity, of course. This will have a force due to gravity as well in this case. Notice that it's not going to be perfectly cancelled out by the normal force here. So we will have to consider that. So we'll immediately have to identify the two different masses we have here, m1 and m2. Commonly also done as m1 or lowercase m versus capital M. Okay? And I'll choose to adhere to that convention here. Does it matter? No, not really. There are formulas that sometimes you'll see lowercase capital M. They're just talking about two different masses. Generally, the capital M used for the larger mass, but not necessarily. Okay? M1, M2, MA, MB, MM, MG, whatever the hell you want to call them, it doesn't really matter. All right? Now, of course, there's going to be this applied force, as we spoke about last time, is going to be essentially the tension force. Okay? That will be applied by the hanging mass over a frictionless pulley system. But the tension force doesn't matter here. We don't actually care about the tension force. All we're imagining is one system of two big masses, but gravitation's effects are going to be different. So there's going to be some force of gravity upwards because this is pulling against that force of gravity. Okay? So we're going to have force of gravity on M, lowercase m, battling against the force of gravity on uppercase M. This here is only going to come from the the parallel component of the gravitational force. All right, don't need to copy that part, sorry. I just want to remind you that we need to imagine this as one sort of fixed system. Okay, so dragged upwards, 20-degree incline by a applied force provided by a hanging mass over a frictionless pulley system. A filled cart has a mass of 750 kilograms. So this M is given to us as 750 kilograms. And they clarify that that's 3 sig figs by giving us the decimals like that, 7.50. They didn't have to include that 0. They chose to, so it's important. It's a significant figure. And the frictional force is 1,036 newtons. That is the frictional force of this cart. Now, which way does that act? Pause and have a think about this. The cart is being dragged up the incline by an applied force. Which direction would the frictional force act? Would it go that way or that way? Show me your hands. Saturday Night Fever? No? Have a think about it. Which way is friction acting on lowercase m if this is a cart being dragged up an incline by an applied force? That way. Yeah? Always acts against motion, all right? Friction always acts against motion. So the surface is stationary, this other object is sliding up it that way. Obviously, a cart's on wheels, so it gets kind of complicated and weird like that, but we don't care about that. We're given a frictional force acting in this direction, FF. Okay? And we know that FF is equal to 1,036 newtons. And that's with 4 significant figures, obviously. I won't bother writing it. It should be clear. Now, the hanging mass, mass 2, again, we've chosen to refer to it as capital M in this case. Doesn't really matter. Capital M is 383 kilograms, and we're asked to determine the motion. So what are we actually being asked? Right, find acceleration. Now, they say the acceleration of the cart, right? So the acceleration of this mass here. Realistically, it's the acceleration of the whole system, right? Because the whole system is going to accelerate together. It's not like this is going to accelerate at one speed and this is going to accelerate at a different speed. That's one of the interesting things about tension in ropes. When you use them to join an object, generally the objects are then going to move at a same acceleration. That's why we can think of it as one entire solid object. Okay, what's going to help us find A? What's immediately the formula we know is going to be very useful here? Gravity, yeah, force due to gravity. We've got that here, right? Is that what you mean? Yep. Okay. Do we want to calculate that to start with? It's probably going to be useful, that force of gravity, so let's find that. Fg equals mg. We're very familiar with this by now. Our mass is, of that one, 383. Our acceleration due to gravity is negative 9.8. Again, we're using the convention of downwards being negative here. That is going to get a bit messy when we start talking about, this friction is technically acting upwards because of the pulley changing the direction here. Yeah. You can think of it like your frame of reference is actually being changed along this pulley as well. So the frame of reference actually turns as it crosses this pulley. Yeah, exactly. Yeah. Yeah. Okay. Again, that's conceptually difficult. So if you're struggling with that, please let me know. We can talk about it. What does this one give us? 3,753.4. Let's go for sig. Let's keep the decimals for now because we are actually going to give a final answer in sig figs. We'll keep as many decimals as we can as we're working out here. Okay, so that's that. Force of gravity. Cool. What else would we do? What else is useful here? F net, right? Again, we want to know A. We're definitely going to use F net equals MA, okay? Now, in the end, the net forces are going to be gravity, friction, and what? Huh? FA? The second gravity as well? Right. So let's think about the net force that's going to affect the motion of this car. It's not going to be moving up and down on the plane. We're not going to have a perpendicular component here. What other force is going to be involved here? What about the gravity? I know I'm going to have some gravity down like this, yeah, but that's not going to be... Right, we're looking for that parallel component of gravity. So Fg parallel, that's going to be relevant, this here. And our net forces are going to be the force of friction plus the force of gravity parallel. So now, what's this FA? The applied force. Where's the applied force coming from? Right. So this Fg here is going to be this applied force. That's all we need to think about it. We can just move this all the way down here. That is the applied force. It's coming from gravity. We don't even need to consider this point. We can imagine this as one solid object. There's a pull on this end. There's a resistance on this end. We accelerate that way. How do we do so? According to the difference in forces from subtracting the force due to gravity. Or we should say, because we're adding net forces, we're adding the force, but of course we know it's going to end up being subtracted because it's negative. Sorry, I should be more correct about that. We're calculating net force, we take the sum of all forces, we add them together. Now that's going to be equal to the mass of the whole system accelerating, right? We're imagining this whole thing as one object, so we need to consider the mass of that one object, which in this case is those two masses added together. All right, let's think. Which of these do we know? We definitely know... Oh, change of color. We know our low mass, we know our large mass, although actually we've got that backwards in this case, but again, that doesn't really actually matter. We don't know acceleration, that's what we're trying to find. We know that Fg, we don't know that parallel component of Fg, and we know friction. So what are we going to do next? Parallel component of Fg, yeah? Okay, so we'll go, I'm going to try and coordinate this a little bit. I'm going to get rid of this little step that I wrote because I was just making a point about how often you're going to be drawing diagrams of these things. We'll go over here now, okay? Go. We started with this. Nope, we started with this. This was our first thing. This was our second thing. This was our third thing. We're now doing our fourth thing. Sorry, I know it's a bit sporadic. Trying to keep track of everything we're doing here. All right, find FG parallel. Now, we're so good at this by now, we just know that FG parallel is just the parallel, which is the sine of our FG. Did I get that right? It's the sine that causes the perpendicular component. Cool. So FG parallel will equal our force due to gravity. What's our force due to gravity? We actually haven't calculated it for this object. We should fix our notation here too. And I started saying that before, and I actually didn't finish that thought. We know that these FGs are going to be acting on separate masses and behaving in different ways. They are not the same FG. So let's call this FGM, and this one FG capital M. Okay, they are going to be different. So this was FG capital M. So this here was FG capital M. This is FG lowercase m parallel. It is important that we separate those out and identify that they're not the same. Not just for our own working out, because we don't want to confuse ourselves and make mistakes, but to be clear about it. Okay, we know FG is just going to be mg, in this case lowercase m, times by the acceleration due to gravity, and sine of 20 degrees. Our lowercase m is 750 times by negative 9.8 times by sine of 20. Check that into a calculator. 2000. Yeah, let's talk about that in a second. 2,530.13. Oh, thank you. 0.8. Let's go 85. Again, in that calculator, you should be carrying as many of those decimals as you can into your next calculation. For the point of showing our working out, a couple of decimal places is sufficient. And then significant figures will come in at the end to round things down. Now this here is going to be in newtons, of course, and as Alex identified, we should get a negative number here. Now this, in this case, is acting to resist gravity, okay? So equals, as we could say a little blurb, as this opposes gravity, make it positive. So equals, so FG of little m parallel equals 2,513.85 newtons. I think I just went to the next page. No, we're good. And now we know everything we need to rearrange and solve for our acceleration. You can do this in parts. You can do this in one big substitution. Doesn't matter. I'm going to have to go to the next page to do it. So let's just stop and absorb this for a moment and make sure we've got each of these steps right, because it's a bit all over the place, and I know you guys are trying to copy down and listen and interpret. So let's go through it from beginning to end now, make sure we've wrapped our heads around it. Then we'll go to the next page, do the substitution, and get a final answer. Okay. So remember, go all the way back to the start of this question. Yeah, we got that diagram down where we imagined the situation we're describing, and we notice that we're looking for acceleration. We connect that we're looking for acceleration with that net force formula. F net is going to be equal to ma. Okay? As soon as we make that connection, we know we're going to need to calculate all of the net forces, all of the forces involved in the acceleration in the direction we're interested in. Now that does not include the perpendicular direction. We're not looking for an acceleration up or down off that plane. It's also not vertical or horizontal acceleration we're looking at. We want to set our frame of reference to be parallel to that plane, and because of that pulley, we need to include in that, in a one-dimensional line, that gravitational force. Now, you could set the gravitational force to be positive, going to the right. You could imagine the gravity is going off like this, continuing up this way, like the applied force. You could imagine that's your gravitational force, and your friction's acting against it. That's fine. You could set gravity to be positive, friction and gravity due to the parallel component to be negative. Doesn't really matter. But we decided to say gravity was negative, the friction and the parallel were positive, and we solved accordingly. Okay. If we've set our frame of reference to be that direction is negative, which we have by choosing gravity to be negative, what's our acceleration going to be, positive or negative? Negative, right? So when we get a negative acceleration at the end of this problem, we're just going to state up the incline to be clear about what we mean. Alternatively, you draw a frame of reference on there which shows that that's positive, or that's negative and that's positive, which is against convention but is allowed. You're allowed to tell me that up the incline is negative, down the incline is positive. That's often more useful because it's more common that things are going down an incline, right? Okay, are we with me so far? Questions about that sort of identification of the net force, identification of that parallel component that we're looking for? Guys, off and away in your bags, thank you. No questions about that? I'm seeing a lot of people who are a bit, like, look genuinely kind of upset about this. Is everything okay? A different answer to which one? Yeah, check radians. The age-old radian problem. I'm pretty sure that's correct. It makes sense. Because the gravitational force is about 7,500. You get a small portion of that going parallel. So 2,500 makes about sense. Okay, so we took that realization that we needed this huge net force calculation. We were missing that parallel component of our gravitational force. We calculated very easily the gravity of the mass, which is our applied force in this case. We found that parallel component using our FG sine theta very simply, and we then added that in. So let's go on and do that now. Let's find our acceleration, okay? So I'm going to take just this part here, and go to the next page. Force of friction plus force due to gravity on mass m that is parallel to the plane plus force due to gravity of the other mass, which is equivalent to the applied force in this case. And that will equal our mass, which is the two masses added together times by the acceleration, which we're trying to find. So we're going to have to divide both sides by m plus capital M to isolate that A. It will cancel on that side, and we'll divide this whole thing by m plus capital M. Or m plus m1 plus m2 if you decided to use that convention. Either one. Now, can you guys help me out? What was the frictional force that we were given in the question? 946? 1036. What was our gravitational force in the parallel component? 2,513 point, what was it? 285? Yep, and what was, and I'm going to fix up positives and negatives in a second, okay? So pay attention for that. I'm leaving a bit of space here if you're copying down as I go. And what was our gravitational force due to our hanging mass? Did I get that right? 0.4. Cool. Okay, and all of that is divided by our two masses added, which is, what was our lower mass, lowercase mass? 1,013 kilograms? 113 kilograms? 1,133? 750 was the bigger mass, but the lowercase one. And the smaller mass, 383. Cool. We are almost out of time, so let's smash this out, and then we're done. And that will equal our acceleration. Like I said, we've cancelled on this side. If that algebra is still freaking you out, please, please, please grab me and we can check that out and I can explain exactly what's happened there. This here, positives and negatives. So let's think about this. So again, our friction is acting down the plane. Our gravitational force parallel due to the mass on the plane is acting down the plane. We've decided that that is our positive force. Arbitrarily, we could flip it. It doesn't matter, okay? Our gravitational force is acting negatively is going up the plane. It's the applied force pulling us up the plane. We've set that to be our negative. We just need to solve this. Anyone done it in the calculator? How many sig figures do we want? 3 sig figs? Was that our smallest sig figs? Yep. Yeah, I think so. Other than gravity, but we can assume that to be practically infinitely accurate. So. Either way, it's 1.8, 180. Yeah, let's go to 1.8 because, yeah, we did use gravity as 9.8, not 9.81 or anything like that. That will be our acceleration there. And again, we're going to stipulate, not this, we're going to say up the incline. Thank you guys, the bell's going to ring any moment. Make sure you're ready for the rest of your day. Whew. What an example, hey? That's about as tricky as things will get, so don't freak out. That's a good one. Yeah, that's that one I was telling you about that's really complicated, where you've got an incline, a mass hanging over it. We ignore the tension. You can look at individual, you can look at each mass and how it accelerates according to tension. You can do that as well, but that's messy. Yes.
It says something for meters per second power.
Say again? Meters per second to the power of 3.
Yeah.
Meters per second. I guess it would just be like how much you're accelerating per second. How much your acceleration is changing per second? Yeah, probably not anything particularly applicable or useful, is what I will say.